Hey everyone, welcome back. Today we're going to be doing another video on velocity and velocity constraints. So let's dive right in. What's going on? We have a cart or a car or a vehicle or a box on wheels, however you want to think about it. So front wheel, rear wheel. What is going on with this rear wheel is you have the outer radius, and that's what goes in contact with the road. And then you have an inner radius of the wheel. These are rigidly attached. And then that inner radius is actually geared, and it interfaces with another smaller gear. So the small gear, let's say that's connected to an electric motor, and that electric motor is generating a torque, and that torque creates a constant angular velocity. That's going to make this thing move. The goal is to drive this thing forward. And then the cart is attached to a rope. This rope goes behind it over a stationary pulley. So the pulley itself, the disc, is grounded. The rope goes over the top and it goes down and it loops, and then it comes back up, and then the end of the rope is rigidly attached to the center of that disc. And then down at the bottom, we have a mass connected to it. Okay. So what do we want out of this problem? Let's say that we want the velocity of the block in terms of the angular velocity of the small gear. This is what we want. So what does that mean? That means this gear is going to rotate with some theta dot. I want the velocity of this block in terms of that gear's theta dot. So we're going to do it all symbolically. Consider that in homework problems. In some of the homework problems, they give you actual numbers. We're going to do this whole thing symbolically, and at the end of it, we're going to put it all together, right? We're going to find the velocity of this block in terms of this angular velocity, and then we can, for example, just put in some numbers for the variables, and we can see what happens. So where are we going to start? Let's start by putting our frames on the problem. We know that we need inertial reference frame, and we know that we need some inertial reference point. So for the inertial reference point, convenient place to put it. Well, consider that the cart's going to be translating left and right, so we're going to have to keep track of the translation of the cart. And the block is going to move up and down, and we need to keep track of the translation of the block. So somewhere convenient for that could actually be the center of this pulley. You could put it there. We could put it maybe at the top corner of the pulley. Honestly, we could put it all kinds of places, but I'm just going to drop it into the center of this pulley. Okay, so there's our point in. Now, how many bodies are there? Well, we got the block. I'm going to say let's not model this pulley as a body. Quick comment on that. By not modeling the pulley as a body, we're claiming that this pulley doesn't have any significant inertia and that it's not affecting the dynamics of the problem. In reality, you could have a very large disc there, and consider that when this rope is running back and forth over it, the disc itself is actually turning, so the inertia of that disc does actually affect the dynamics of the problem. For now, undergrad class, so we're just going to take that out. So we've definitely got one body here. We've got the cart, and we've got the wheels attached to the cart, and we've got the little gear. So we could make the cart a body, and make the front wheel a body, and make the rear wheel a body. If we wanted to generate the full dynamics, that is what we would need to do, because consider the wheels have mass and inertia. The cart itself is going to have some kind of mass. For what we're doing, analyzing this, we're still in the kinematics part of our study. So what we can do is we can make this a body, and we can make the cart a body, and we can make the rear wheel, and we can make the gear We don't particularly need to make the front wheel a body. I mean, it's there, sure. But if we assume no slip, then however fast, and we assume that they're the same size, whatever rotation the rear wheel goes through, the front wheel will go through the same. So it's not really going to give us any more useful information. So let's say that, honestly, similarly with the cart, the translation of the cart is also the translation of the wheel. So, that might not actually give us a bunch of new information. That's okay. Let's put this point at the back of the cart. Let's call that point A. Let's make the center of this rear wheel B. The center of this disc is C. And the block, I'm going to keep track of this point where the rope comes down and loops and passes through this little clip connecting it to the block. So let's call that point D. All right, so we got our points on there. We know that we need frames. D frame. D frame is not going to rotate. We're going to assume that this block only translates vertically. So the D frame is going to stay aligned with the N frame. Same thing with the C frame. This cart is only going to move left and right. So I'm just going to say C frame like that. Sorry. That's A frame. A frame. Okay. B frame. Well, the rear wheel, it does rotate. Are there any points on this rear wheel that are important? Not really. I mean, nothing is pinned to the outside of it. There's no joints there or anything. So the direction for the B frame, we can put anything down and it's honestly fine. So B frame, and same story with C frame. This thing's going to rotate, and the specific current angle of it is not particularly important. All right. So we got 1, 2, 3, 4 points. 1, 2, 3, 4 frames. Okay, let's go through and we need to define some position vectors, etc. And tell you what, we got a little space right here. We'll do it here. And I'm gonna erase the D frame. Okay. So let's start by doing the position vector from N to A. So what do we got? We need to do a translation variable in the left and right, and it looks like there might be there's some vertical displacement as well. That's okay. So let's say L1 in the y hat N, that takes care of that vertical displacement. And then of course the cart is going to move, so we've got Q1 in the x hat N. Next, consider that the wheel, if the wheel is moving, if the wheel is translating, then the cart is translating. So there's no relative velocity between points A and B. These 2 points do not move with respect to each other. Assuming that the cart is only going left and right, it doesn't spin or anything crazy like that. So what we can do is we can say the position vector from A to B, and we can similarly do the position vector from A to C. And in both of these cases, these position vectors are actually fixed. So let's say L2x, and just to be a little more formal, let's put it in the A frame, the frame of the cart itself. This definition, putting it in the A frame, this would actually allow us, if we were going to rotate the cart, if the cart's going to do a wheelie or something, this would actually hold it. This would do it in the body frame, and that would hold as well. But like I said, we're assuming that the cart doesn't move, so it actually doesn't matter. We could be doing this in the in frame, and it would be fine. Same thing with going from A to C. This position vector is not going to change, so this is L4xa and L5 ya. Now, one thing to note is that we are not, this part that we're doing right now, we are not using B frame or C frame, the frame of the rear wheel or the electric motor, because those frames move. So if we define this as B frame or C frame, it would not be correct. All right, what do we got to do next? We need to get from point N down to point D. All right, so into D. Well, first of all, the block doesn't actually hang perfectly under point N, right? If this were a real system, there'd be a little width here, and this thing's probably in between these two ropes as they hang down. So, okay, we can add in a little bit of horizontal displacement. Let's say negative L6, x hat N, and then the vertical component, I'm gonna say that, let's go, I'm gonna erase just a little bit over here. And let's say the distance between N and D. There we go. Let's call this one Q2. Now I'm gonna write it as plus Q2 y hat N. We know that Q2 is a variable. If this throws you, if you're more comfortable doing, writing it as negative Q2 because you're going down, by all means, do that. Because this is a variable, it can take on positive or negative values. So the way I have written it, it currently has a negative value. In fact, at all points in this problem, it's going to have a negative value because it cannot go above it. But that's fine. Okay, next. Actually, tell you what, I usually do it this way in problems, just to prove that we can, right? Just to change things up. Let's just make it negative. And we're gonna get the same answer regardless. In this problem, because I have written it negative over there, that means right now the numerical value of Q2 is negative. This is relevant because if you were running some simulations of this problem and it came back and it gave you values of Q's and thetas, etc., if you wanted to animate it, the value coming out of the simulation for Q2, because of how we defined it, is going to be positive now. And then when you go to animate it, you have to remember that it's actually below it. So if you go in, if you're animating this thing in Python or in MATLAB or something, and you want to start drawing some spheres and blocks and cylinders and stuff, you have to give these bodies coordinates. And if you give this thing, if you just take that positive coming out of the simulation, you put it into here, that means it's going to be up. So that's why I usually do all my variables as positive, because whatever numbers come out of the simulation, you literally take those numbers and you put them into your animation, and you don't have to worry about signs. But just to prove that we can, let's do that. All right, so we got the position vectors. Let's do the rotations. I'm going to do my shorthand for the rotations because we've done it so many times. So A frame does not rotate, D frame does not rotate. I'm going to do R into A. And I'm just going to say that this is an identity matrix. We've talked about this in our Teams lectures. And we also, I mentioned it in a previous video talking about rotation matrices. So the A frame doesn't rotate, so it's aligned with the N frame. So I'm just going to say the rotation matrix is I3. And as always, pleasant reminder, do not use this kind of shorthand on an exam or on homework. All right, so the A frame and the D frame do not rotate. The B frame and C frame, those do rotate. I'm going to use absolute angles between them, and we are doing rotations around a shared z-axis. So B frame is going to rotate with theta 1, and C frame is going to rotate with theta 2. All right. So we've got positions and we've got rotations done. We could do our location descriptions. Location description of A, ... And do all four of them. All right. Next, how many generalized coordinates do we have? Well, usual approach is go through and just highlight all the variables. So we've got Q1 and we've got Q2, our two translations, and then we have theta 1 and we have theta 2. We've got two rotations. So we have 4 generalized coordinates. They are Q1, Q2, theta 1, theta 2. All right. Degrees of freedom. by intuition, if we can do it on this problem. By intuition, what's going to happen? We have an electric motor at C. We fire up that electric motor. It generates some torque profile that it's, let's say we've got some sensors on it, and it responds to friction and everything else, and it generates a constant angular velocity. So the little disc is spinning. When the little disc spins, it's geared to the interior of the rear wheel. So that's going to make the rear wheel spin. And when the rear wheel spins, that's going to make it roll, and it's attached, right, through some kind of suspension or axle or something to the cart. That's going to make the cart translate. And when the cart translates, it's going to pull the rope, and it's going to make the block move up and down. So clearly, this system has 1 degree of freedom. So we know what that means. That means we have to go looking for constraints. And in this case, we need to find 3 constraints. All right, so what are those constraints? We look through the problem and we just ask ourselves, does this thing have any gears? Hey, there's one gear interface, so that's 1 gear constraint. Does it have any pulleys, rope pulley systems? No. It does have a rope though, right? This isn't like a belt and pulley like we saw in the previous problem, but it is a rope, and that rope has constant length, right? There's one end of the rope, there's the other end of the rope, and we're going to assume that the rope doesn't stretch. So 2 constraints. The 3rd constraint is going to come from the rolling body, right? As this wheel spins, it's also going to translate. So there's constraint number 3. There's no loop, no vector loop on this one, and no kind of weird geometric stuff. So we just need to write those 3 constraints. So let me clean this up a bit. Let's start with the gear constraint. We have this interface between body B and C. Notice that the little gear C is interfaced with the interior radius of B. So we need to acknowledge that there are 2 different radii that are of relevance here. The inner radius is gonna play into the gear constraint, and then the outer radius is the one that's in contact with the road. So let's say that the inner radius is RA1 and the outer radius is RA2. So what's the gear constraint on this? So the radii of C, so we can say that RC, and the angle associated with the C frame was θ2. This is going to equal RA1, and that's going to be theta, oh, I did B, sorry. This is body B. A was the cart. There we go. Okay. RB1. And this is now θ1. And of course, the relationship between these is going to be negative because it's a gear. So when one rotates positive, the other rotates negative. So there's our constraint. All right. Next, let's do the rolling constraint associated with the wheel. We've seen this before. This is RB2, right? Because we're looking at the outer radius. And then the rotation of the B frame, right? The big disc is body B, and the B frame is what's attached to it. That angle was θ1. And then that is going to be related to the translation of the wheel. So I'm going to write this as Q1, right, plus, God, what length were we up to? Let's just say L8. I honestly don't remember. Now, why did I add a little bit to this? If you recall the position vector from before, we said P into A was Q1, X hat N. That's not actually where this wheel is, though. The wheel's actually a little bit in front of it. But here's the interesting thing that happens with this rolling constraint. You can add some offsets to these if you really need to keep track of positions, etc. But consider, we're going to take derivatives of this. And any offset that you add to this equation, as soon as you take the derivative, those offsets are going to go to 0 anyway. So you can think of, when you're writing these constraint equations, you can keep that in mind, that these things are eventually going to be we're going to take the derivatives of them. Now, in this case, this constraint works just as well without that particular offset. We need to do this rope constraint, and in that one, the offsets actually are quite important because they help you determine the total length of the rope if you were going to go purchase a rope or cable, right? You need to know how long it is. So here's our first two constraint equations. Equation number 1 and equation number 2. There we go. So what about equation 3 now? Equation 3, I'll do it down here. This is going to be our rope constraint. So usually with a rope, what I would do is I would just go through and I would break this thing up into pieces. I would say from this point to this point is one section of the rope. And we've actually already called that out. We said that that's Q1. The next section of the rope, I'm going to do from here to here. And we've called this one out. This one is Q2. And conveniently, right, I made the problem. Conveniently, that is also Q2. Now, there's a little bit of variance here. We know that the rope is kind of bending on bottom, okay? There's also this bit of contact area on this belt up, on this disc, this pulley on top. So what we can do is we could give that an L as well. We could call it, L9, L10, whatever we're up to. I usually just do like a little delta. It's the lowercase Greek letter delta. Capital deltas are used to reference things like delta T, change in temperature. Oftentimes in engineering and science, if you just have some small amount, maybe not like a differential amount, but just some small value, and you just need a placeholder for it, the lowercase delta gets used often. So if you see that, that's what it is. So let's do a rope constraint. We just need to take these pieces and add them together. These are going to equal some constant. Let's call the constant K. So K being the length of the rope. What is the length of the rope? It's Q1 plus Q2 plus another Q2 plus this little bit delta. And you might have these little deltas. You might have a whole series of pulleys that your ropes pass through. And you can find that just by going look at the geometry of your disc. Now, an interesting point in this, this length, right? This length is Q2. And the way that we define Q2 is that this value right here is positive. An interesting thing that would have come out of this, if we needed to measure this distance, it would have been negative earlier. But consider because we changed how we define the position vector, now the Q2 has a numerical positive value. So adding it is consistent. If we had defined it in a way that Q2 had a numerically negative value, then we would have needed to subtract over here, negative to make it positive. Because this distance is not taking away from the length of the rope it's adding. So sometimes when you do constraints, depending on how you define your position vectors and stuff, just take those things into account and make sure all the logic is consistent. So here's our 3 constraint equations. So we had 4 GCs, we have 3 constraints of the 1 degree of freedom. All right. Let's say that the homework problem tells you that this thing is rotating, so that's going to be theta 2 dot. Let's say that this thing is rotating at 3 radians per second. All right. So we said, remember that we want the translation of this in terms of the rotation of the disk. So ahead of time, what we're looking for is we're looking for Q2 dot as a function of theta 2 dot. That is what we need in order to solve this problem. So how are we going to connect all this stuff? We haven't even taken derivatives yet, so we don't have dots anywhere. We're going to. Where is Q2 in all of this? Here's the Q2, right? Q2 does not appear in either of these equations, so the only way to get Q2 is to use equation number 3. In this equation, if we want to solve for Q2, then the length of the rope and the delta, these are both constants. So the only other variable here is Q1. We have to define, we have to solve for Q2 in terms of Q1, which means we have to solve for Q2 dot in terms of Q1 dot. Okay, how do we get Q1 dot? Remember, the input to the problem was theta 2 dot. Well, I can get Q1 dot using equation number 2, right? And that allows me to solve it in terms of theta 1 dot. And how do we get theta 1 dot? Well, that comes from equation 1, right? I can solve for theta 1 dot in terms of theta 2 dot. And hey, look at that. That was our input, right? So when you're working these problems, if you have some information, but you need other information, you need the value of other variables, that is where the constraints come in. They help you, they allow you to solve for these unknown variables in terms of the knowns. Or we could say the dependent variable, we have solved for it in terms of the independent variable. All right, so how do we do that? What I would recommend, before we jump right into the taking derivatives of constraints, I think it's always a good habit to define angular velocities. So omega into A and omega into D, these are both 0. Omega into B, this was our theta 1 dot, and that is Z B. And then omega into C, this was theta 2 dot ZC. Okay, that's easy. Get that out of the way. All right. Now recall that the problem said that we want the velocity of the block. Take note of that language. If we want the velocity of the block, remember that velocity is itself a vector. The velocity of the block is not Q2 dot, okay? It's almost Q2 dot. Q2 dot is a scalar. The velocity is a vector. That means that you do have to formally define VD. So VD is ddt of P into D. We know this, and you can go back and you can look at those position vectors. And of course, VD is going to come out to be, we defined it negative Q2 dot, Y in. Don't forget that. It's kind of the whole point. All right. So angular velocities, linear velocities, knock all those out. So at this point, once you've done all your angular and linear velocities, now we can move on and we can take derivatives of constraints. So let's do that. I'm just going to do them, let's box these in, and I'm going to write the derivatives of constraints right underneath. So ddt of equation number 1, RC theta 2 dot equals negative RB1 theta 1 dot, okay, and RB2 theta 1 dot equals Q1 dot. All right, quick comments on this. We didn't check a moment ago. Let's check it now. When on B frame, when theta 1 is positive, that means that the cart is actually rolling to the left. We saw this when we first derived this constraint. So let's add a negative to this. So negative Q1 dot. There we go. So here's our constraints. Here's our derivatives of our constraints. We got to do the same thing over here. What's going to happen in this one? Well, K is going to go to 0 and the delta is going to go to 0. So we're going to have 0 equals Q1 dot plus 2 Q2 dot. Let's rewrite that. We know that we're going to have to solve for Q2 dot. So Q2 dot is equal to negative 1/2 Q1 dot. So what does this tell us? That equation says that if you have a positive Q1 dot means that the cart is moving to the right, yeah? And if the cart is moving to the right, just by intuition, the block is going up. So this equation tells us that if Q1 dot is positive, right, then Q2 dot is negative. Q2 dot is negative. That's interesting because the block is going up, right? The block is going up. But remember, we did a little experiment on this one, and we defined the position vector into D as negative Q1. So, if it's negative Q1, that means you're measuring it, right? That means the value of Q1 is instantaneously positive, and then we take the negative of it, direction. We could write it this way, Q1 in the negative y hat in. That might make a bit more sense, right? We're measuring it as Q1 in the negative direction. Well, according to this equation, for a positive Q1 dot, that makes this negative, right? So that means the value of it is becoming more negative. And that means the value of this Q1 right here is going to get more negative, which means it's going up, right? So maybe in some problems there's no best or perfect way to do it. This is why when I work these, I have just trained myself to always do these things as positive. And then if I have to sort something out in a constraint equation somewhere else, hey, that's okay. I like to always define these things positive because when I get to this level, when I get to the velocity level, it makes sense for, if Q2 dot is positive, that means it's going up. If Q2 dot is negative, that means it's going down. Because of how we defined the position vector, that is not true. Because we put a negative on it, a positive Q2 dot means it's going down, and a negative Q2 dot means it's going up. So you, as the engineer, you have to keep track of all those definitions. You just do, there's no good way around it. All right, so let's put a box around this equation. So we had 3 constraints, 1, 2, 3. We have 3 velocity constraints, 1, 2, 3. At this point, we can start combining all this stuff and we can put it together. So what I'm going to do, I want to leave this math, so I'm going to erase the diagram. And we can redraw it again if we need to, but what do we need to do? Clearly we need to solve, we got the Q2 dot, that's good. Over here, in this equation, we can just move the negative, boom, done. And we can take this and we can put it in there. So let's say that Q2 dot is equal to, negative and negative is going to make this thing positive, so 1/2 RB2 theta 1 dot. Okay? Let's take the equation right above it and let's solve for the theta 1 dot. And I'll do it down here. Theta 1 dot equals, move the negative to the other side, RC divided by RB1 theta 2 dot. We can take this, we can put it up here, and there's, oh, don't forget the negative. There we go. Okay, Q2 dot equals 1/2 RB2 multiplied by negative RC over RB1 theta 1 dot. And let's combine this thing and clean it up just a little bit. And let's say that Q2 dot equals 1/2. Let's put the negative in front. Negative 1/2 RC over RC RB1. That's 2 over RB1, there we go. Multiplied by theta 1 dot. All right, so let's check this out and let's see if we agree. Here was the drawing. I'm gonna just do it fast. There's the wheel, there's the cart. Okay, and then there's the rope and the block is down here. All right, let's take, let's say that this thing has a positive spin coming off of the electric motor. That positive spin on the small disc is going to create a negative spin on the rear wheel. A negative spin on the rear wheel is going to push this thing forward. And when it moves forward, the block is going to go up. So if we take a positive value, right, positive angular velocity on the gear, we have this, this kind of chained gear ratio now, resulting from the electric motor being on the inner radius and then the outer radius being in contact with the road. We have the thing because of the looping, and then we put a negative on it. So if theta 1 dot is positive, we get negative Q2 dot. And remember a minute ago, because of how we defined it, a negative Q2 dot means that this thing is actually moving up. So what would have happened if we had left the original definition intact and we had just done P into D as positive, Q2 and the Y hat in, and we just, like we always do. What would happen is you would have had to change your rope constraint by putting negatives on the Q2s, okay? Those negatives on the Q2s would have rolled their way all the way through the math, and at the end of this process, we would have just had this relationship. And this honestly seems a little more intuitive. You give me a positive spin on the little gear and a negative spin on the big gear and a positive translation on the cart, then this block is going to positively move up. So that is, again, I've just learned this from experience. That is why I like to do things like this. Okay, I know on a lot of your homeworks, they give you numbers. So if you're working a problem and numbers are provided, then you need to crunch those numbers and you need to give me a numerical value. Now, the part I actually care about is all of this, all of the analytics. And that's the only thing that's going to be on exams. It's going to just be some symbolic stuff. So let's put some numbers in it as if this were a homework problem. We said earlier that we could do, we said theta 2 dot was 3 radians per second. So RC was the little one. So let's say that's 2. RB1 was the interior radius. Let's make that 4. And RB2 was the outer radius of that rear wheel. Let's make that one 5. Okay. Q2 dot is going to equal, and you literally just come in here and you put the math in at the end. So 2 multiplied by 5 divided by 2 multiplied by 4 multiplied by 3. That's literally it. Do all of the analytics first and then just come back at the very end and you put the numbers in on the math. So what are we looking at? 15 over 4. So 15 over 4 is 7.5 over 2. So 375. Okay. Okay. Cool. Yeah, that's it for this one. We're gonna do some more videos. We've got like a whole week left where we're just gonna keep practicing some velocity problems because this is honestly one of the most important steps in the whole process. If you can get this down, then you'll be able to handle the acceleration portion very well. And we're going to continue doing this the whole semester anyway, so you might as well get it down now. Okay, that's it for this video. I will see you next time. Best of luck.